Welcome back to the Cisco NetAcad CCNA3 Enterprise Networking, Security and Automation lecture series. If you haven't seen my previous lecture series covering CCNA1 and CCNA2, I will leave links in the description for those playlists. I would recommend that you go through the previous CCNA lectures before you move forward with this course. Today, I will cover the penultimate lecture in this series, which is module number 13, Network Virtualization. In this module, we will learn the purpose and characteristic of network virtualization. We will cover the topics of cloud computing, virtualization, virtual network infrastructure, software-defined networking, and the controllers. Cloud computing. There's a video called Cloud and Virtualization available to you through your Cisco NetAcad. However, if you do not have access to this video, I have a copy posted to my YouTube channel, and I will leave a link in the description of this video as well as a card on the top right hand corner. I would recommend that you watch this video before you go through the next few slides. Cloud overview. Cloud computing addresses a variety of data management issues. It enables access to organizational data everywhere and at any time. It streamlines the organization's IT operations by subscribing only to needed services. It eliminates or reduces the need for on-site IT equipment, maintenance, and management. It reduces costs for equipment, energy, physical plant requirements, and personnel trainings. It enables rapid responses to increasing data volume requirements. So the cloud computing would allow an organization to outsource their IT operations and pay for what only needed, and it also make them easier for scalability as well as availability of data and services. So those are key features of cloud services. So let's look at the cloud services. The three main cloud computing services defined by the National Institute of Standards and Technology, also known as NIST, in the special publication 800-145 includes the software as a service, also known as SaaS, which is the situation where the cloud provider is responsible for access to applications and services that are delivered over the internet. Platform as a service, also known as PaaS, is a situation where the cloud provider is responsible for providing users access to the development tools and services used to deliver applications. The infrastructure as a service, also known as IaaS, which the cloud provider is responsible for giving IT managers access to the network equipment, virtualized network services, and supporting network infrastructure. Cloud service providers have extended this model to also provide IT support for each of the cloud computing services, also known as IaaS. For businesses, the IaaS can extend the capability of the network without requiring investment in the infrastructure, training new personnel, or licensing new software. So you can view this as a different types of services or tiers of services that you can obtain through the cloud service providers. And on the next slide, I will give you a broad overview of that so that you have a better understanding of these three different types. So this is not a part of your Cisco NetAcad slide set. So if you get access to these slides through your academic institution, this slide is not there. This is something that I have added because this image gives you a broad overview of what we just discussed. So here is the cloud computing models. As I mentioned, it is IaaS, PaaS, and SaaS. And it shows anything that you control in blue, and anything the service provider control in orange. So if you have all your IT services, servers, everything, software, hardware, any other applications that you are running, virtualization models, everything in your own site, and there is no outsourcing at all, what's going to happen? You will be responsible and managing and controlling the infrastructure for applications, data, runtime, middleware, operating system, virtualization, servers, storage, and networking. So everything will be your responsibility. As you move down the models from left to right, the responsibilities start shift towards the cloud computing companies. Like for example, in ISaaS, the virtualization, server, storage, and networking is not your problem because they are provided to you by the cloud service. And as you move to all the way to the right, when you go to the SaaS, where software as a service, everything from networking, storage, servers, all the way to the application itself is completely managed and handled by the cloud service provider. So here is an example of that. So if your company is using Google Docs for enterprise, the Google Docs for enterprise is completely software as a service. So you don't have to worry about any of these things. You are paying for the Google Excel, Google Word, Google PowerPoint for your business, and it is completely handled by them, and you don't have any of these things to worry about. As opposed to if you have your own server and you have installed, let's say, a Microsoft Word, Excel, PowerPoint at the server level. No, I'm not talking about the Office 365, but I'm talking about the server level Microsoft Office. In that situation, you will be responsible for not only for the application and everything else going with it, but also the hardware and everything that needed, networking, storage, everything that needed to be there in order for you to run the same sort of services. So this is a really good overview, and I didn't make this diagram. It was taken by this bmc.com/blogs website. So if you would like to take a look at this in more detail, you can go in there, but this will give you a broad overview of what we have just covered in the previous slide. Again, this is not part of your Cisco curriculum slide set. This is something I have added to enhance your understanding about differences between ISaaS, PaaS, and SaaS. Okay, so this will be making it easier for you to understand the concepts that we covered in the previous slide. So let's look at the cloud models. So there are 4 primary cloud models. They include public clouds. So those are cloud-based applications and services made available to general population. Private clouds, those are cloud-based applications and services intended for a specific organization or entity such as government. So those includes things like if the government entity buy Office 365 from Microsoft, and the Microsoft can provide that Office 365 capabilities in a private cloud for the government, as opposed to Office 365 free versions may be available through Microsoft to the home users, or the Office 365 paid versions provided to home users where they shared the cloud service with other paid users. So they can do private cloud for security purposes, especially for organizations such as governments. Hybrid clouds, that's a cloud that is made up of 2 or more clouds, for example, part private, part public, where each part remains a separate object, but both are connected using a single architecture. So you have a public, partly public and partly private system. They are, however, using the same infrastructure and architecture to connect to each other. Community clouds. A community cloud is created for exclusive use by a specific community. The difference between a public clouds and community clouds are the functional needs that have been customized for the community cloud. So a community cloud is like a public cloud, but it is not really a public cloud because it has been customized. So for example, healthcare organizations must remain compliant with policies and laws such as the United States privacy policies, and that requires special authentication and confidentiality, hence creating those community clouds. So in Canada, for us, community clouds also includes inter-university clouds that we exchange our research data and information. Those are secure clouds. They are technically not private clouds because they are still community clouds where all the university researchers from different government and semi-government research programs join together. Community clouds also include healthcare in Canada as well. For example, Alberta Health Services Health Link Network, where doctors and nurses access your medical record through electronic means, is the type of a community cloud as well. So the difference between a community cloud and a public cloud is that the community cloud is customized to provide security and other policies applied to it to make it safer and secure and better than just open public cloud. Cloud computing versus data center. These are the correct definitions. So sorry, I would say these are the correct definition for data center and a cloud computing as of now, because the reason that the cloud computing is also kind of evolving at this moment. So data center is typically a data storage and processing facility run by an in-house IT department or leased off-site. So you can lease space on a data center if you wanted to. If you are a medium to large corporation, instead of building your own data center such as Facebook or Twitter or Google, oftentimes most corporations would actually just lease the data center space from a third-party company. Data centers are typically very expensive to build and maintain, and that's why people oftentimes lease. Cloud computing, however, is typically an off-premise service that offers on-demand access to a shared pool of configurable computing resources. These resources can be rapidly provisioned and released with minimal management effort. So that is the current definition of cloud computing. But in my opinion, that I think the cloud computing evolving is so fast, the definition may change even within the next few years. So for now, what we call today a cloud computing is typically an off-site premise where services and offers on-demand access to a shared pool of configurable computing resources are provided, and these resources can be rapidly provisioned and deployed with a minimal management effort. So that's what makes a cloud computing in modern day. Data centers are the physical facilities that provides the compute, network, and storage needs of cloud computing services. So cloud computing services still need data centers. It just happened to be a different types of data centers. So cloud service providers use data centers to host their cloud services and cloud-based resources. So we are not taking the data centers out of the equation completely, but what we are doing is we are reinventing how the data centers and computing works in this situation. So keep that in mind, because sometimes if you had no knowledge in computer science, or if this is your first couple of courses that you are taking in computer science, you may get the misinformation, like a confusing information that cloud computing somehow eliminate data centers, but that is not what is happening. Cloud computing is making it easier to have a shared pool of configurable computing resources, but it is not actually eliminating the data center itself. So for your exams and quizzes for this particular course, if you are taking through Cisco NetAcad, these are the two definitions you should remember, but keep in mind that cloud computing is a highly evolving, cutting edge technology. So things might, the definitions and what is encompasses as cloud computing may change over time, especially with artificial intelligence and a whole bunch of other things. So also keep in mind, as I mentioned, cloud computing does not eliminate the need for data centers. It just make it different. You make a different use of it. Virtualization. Cloud computing and virtualization. The terms cloud computing and virtualization are often used interchangeably. However, they mean different things. Virtualization is the foundation of cloud computing. Without it, the cloud computing as it is most widely implemented would not be possible. So keep in mind, the virtualization is not the same as cloud computing. Cloud computing uses the virtualizations to offer those services through those cloud computing mechanisms. So keep that in mind. Virtualization separates the operating system or OS from the hardware. So the whole point of virtualization is separation of the operating system from the hardware. So the various providers offer virtual cloud services that are dynamically provisions servers as required. These virtualized instances of servers are created on demand. So those include Microsoft Azure, Amazon, AWS, etc., etc. So those are on-demand services where you would be able to create virtualization instances for your organizational needs on those platforms. Like Microsoft Azure, you can spin up a couple of virtualization instances for whatever the needs you need, for example, for email server, file server, etc., etc. So virtualization can also be done on your own computers using like desktop applications such as VMware Workstation, for example. I have few videos on my YouTube channel on that. Or VirtualBox, which is a free version that is available for virtualization, as well as ESXi, which are like the type 1 hypervisors, which I will describe later in this series, in this lecture. There are different types of virtualization, but however, what the virtualization is doing is separating the operating system itself from the hardware. So that's the key definition of virtualization. Virtualization is needed to run cloud computing services. However, the virtualization is not exclusive to cloud computing services. So you can actually have a virtualized environment built on your home desktop computer using programs such as VirtualBox or VMware Workstation, for example. So keep that in mind. So even though you may hear the term cloud computing and virtualization interchangeably, even though I haven't heard that a lot, but Cisco says it is right here, and the terms may be interchangeably used, it is not the same. So keep that in mind. So cloud computing needs virtualization, but virtualization doesn't need cloud computing. You can run virtualization almost on any hardware actually. Dedicated servers. Historically, enterprise servers consisted of a server OS such as Windows Server or Linux Server installed on specific hardware. All of our servers' RAM, processing power, and hard drive space were dedicated to service provided. So for example, web, email, etc. services are installed. So historically, those enterprise servers, what they're going to do, they're going to install a server operating system on that hardware, and it could be either Windows Server, Linux server type of servers. And then what's going to happen is all of the server's RAM, processing power, and hardware will be used by that operating system as a result of that dedicated hardware. So when a component fails, the service that is provided by the server become unavailable, and this is known as a single point failure. Dedicated servers were generally under use because what happened is they often sat idle for a long periods of time, waiting until there was a need to deliver the specific service they provide. So these servers wasted energy and took up more space than was warranted by the amount of service provided. This is known as server sprawl. So server sprawl is a huge problem with the dedicated servers, because imagine you have a company, a small business, and you build a dedicated server, but let's say you have your work usually done on Monday to Wednesday, and after that not many people access those specific particular files in that server. So that server going to sit idle for most of the week, including weekends. But you still need to run that server because maybe your boss need to randomly access some of the files, let's say through FTP, to gain access to certain files even on Saturday. So servers keep running 24/7, but in reality the server is only either used by Monday to Friday or Monday to Wednesday, the peak times. So that what caused the server sprawl. So basically in the dedicated server, what happened is the CPU, memory, NIC, disk space, everything is dedicated to whatever the services they are providing. And when it is not fully utilized, what's going to create is something called server sprawl, which is such a waste of energy and resources. One thing I want to keep you in mind is that in this example, Cisco is showing that the web server, email server, SQL server, file server, DHCP server, ADDS, AAA radius, and NMS as showing as separate servers. But we would almost never do that in the industry. A Windows server, for example, have the ability to run the email server, SQL server, file server, DHCP server, ADDS, AAA, etc., all in a one single hardware. But still, that you will be spending money on that dedicated enterprise server that may not utilize all of its capabilities to its maximum most of the time, causing server sprawl. But you don't need a dedicated server per service like is shown here on this diagram. Just keep that in mind. And again, I will go through these in detail when I'm doing my lectures on server hardware and my lectures on client services and client servers later sometime. Server virtualization. So the server virtualization takes advantage of idle resources and consolidates the number of required servers. So as opposed to having dedicated servers where they might create idle situations, a waste of space, waste of resources, the virtualization, basically what it's going to do, it's going to consolidate all of those required services and servers into something that more efficient. So this also allows for multiple operating systems to exist on a single hardware platform. So that is one of the key features of virtualization. It allows you to share your existing hardware with multiple operating systems. The use of virtualization normally includes redundancy to protect from a single point of failure. The hypervisor is a program, firmware, or hardware that add an abstraction layer on top of the physical hardware. The abstraction layer is used to create the virtual machines which have access to all the hardware of the physical machines, such as CPUs, memory, disk controllers, and network interface cards. So this is a key piece of information you should remember for exams and quizzes. If somebody asks you what is a hypervisor, basically hypervisor is not a virtual machine. Hypervisor is a program or firmware or even a hardware that adds an abstraction layer on top of the physical hardware, which allow the the system administrators to create virtualization environments. So hypervisor is a program, firmware, or a hardware that adds the abstraction layer on top of the physical hardware, but it is not the virtualization itself. We are using hypervisor to create the virtualization. Keep that in mind. So on the right hand side, we have two examples, server 1 and server 2. In server 1, we have the hardware, then we have the hypervisor on top of it, and we have multiple instances of Windows OS with the different services installed here. And in the server 2, the same thing. I believe what they're showing is the multiple instances of Windows OS with the different services installed there. Again, if I were to do this nowadays, I wouldn't install multiple instances of the Windows Server OS. Instead, I will install one Windows OS and install all the services on top of that, all of these ADDS and Radius and HDHCP. But however, maybe I want a Linux instance, and I can actually install Linux instance on this hypervisor, because this hypervisor is providing that abstraction layer between the hardware and the operating systems that we are installing on top of that. So keep that in mind. So this is a really poorly done diagram actually. These are really poor examples. I don't know why Cisco give it this to you, because if I'm going to show you this, what I would show is I would put ADDS and Radius on top of all of this. So one Windows OS will have these two, and maybe make this thing Linux and make this thing a something else like a DNS server, for example, DNX Linux server. So you can put different OSs. You don't need to install the same Windows server instance, multiple instance on top of your single hypervisor, because I don't know why anybody want to do that. Maybe as a backup. So keep that in mind as well. Again, I will go into much more in depth and detail about these on my server lectures, but for now, for this particular course, that's all you need to know. Advantages of virtualization. So one major advantage of virtualization is overall reduced costs. Remember, you have the ability to install multiple operating systems and softwares on top of that hypervisor, right? So as a result, it is less equipment is required, less energy is consumed, because you can use the same server for multiple instances of operating systems and services, and less space is required as well, physical space too, because you can use that one physical hardware to do all your work. These are additional benefits of virtualization. They include the easier prototyping, faster server provisioning, increased server uptime, improved disaster recovery, and legacy support. So for easier prototyping, let's say you have a server with specific configurations on a Ubuntu or machine, right? Or Ubuntu or CentOS machine, right? It's a Linux machine. And you want that a particular configuration to be backed up and reused again and again and again. You can do that with virtualization very easily, because you can make a copy of that virtual machine and keep reusing it. So that's what it means by easier prototyping. Prototyping basically means you can take a copy of a virtual machine, even a Windows server, and you can put it into multiple, you can spin off multiple instances. Again, I will go into caveats associated with that, especially with if you have domain controller installed on your VM. Prototyping is a really bad idea. You should never copy domain control virtual machines. I will explain why that is on a different video again, but what they meant by easier to prototyping is basically you can use a one VM instance, and you can take copies of that for other instances, and making it easier for you to replicate things. And faster server provisioning. So as a result of that, you can, you save time. You don't have to start from scratch every single time you need to spin off a new server. Increased server uptime. So one of the advantages of virtualization is that by having that portability, you can increase the server uptime as opposed to having a physical dedicated hardware server. There may be more downtime because of the other issues, such as hardware issues that you may be facing. Because if you have a hardware issue on a virtualized environment, you may be able to quickly migrate that virtual machine to a new hardware with a very little downtime. Improved disaster recovery, again the same thing. You can back up your entire virtual machine to a different disk or even a different offsite thing, and as well as legacy support. So there are situations in your career that you will come across some softwares that may not run on, let's say, Windows Server 2019, but would run on Windows, like older version. So you can spin off an older version that may not be as secure as the Windows Server 2019 or the 2021. The new one, I believe, is 2021. But however, by using those virtual machines, you still can provide support for those software, right? By creating those legacy operating system support on virtual machines. Abstraction layers. So I mentioned abstraction layer a little bit in the previous slides. So a computer system consists of following abstraction layers. They include the services, operating system, firmware, and hardware. Those are called abstraction layer. At each of these layers of abstraction, some type of programming code is used as an interface between the layer below and the layer above. So just like a hypervisor, which is also a type of abstraction layer, that provides the communication between the hardware and the virtualized machines. Even with the things like services, OS, firmware, and hardware, each of these layers, abstraction layer, some type of program code is used as an interface between the layer below and layer above. So that's how they communicate against each other. A hypervisor is installed between the firmware and the operating system. The hypervisor can support multiple instances of operating systems as a result. So remember that the hypervisor is installed between the firmware and the operating systems, and the hypervisor can therefore support multiple OSs, as I mentioned before. So on the bottom of the screen, that's what it's showing. So we have a typical server. This is like a dedicated server where we have hardware, firmware, operating system, and then you run the services. So that is a dedicated server with multiple services on a one single operating system. Let's say Windows Server 2019 with the web, email, and file services. But in virtualization environment, what happens is you have the hardware just like here, but now you have a firmware, and on top of that firmware we have a hypervisor that is allowing us to have multiple different operating systems on top of that hypervisor that would allow us to run different services on those different server segments. So I mean virtualized environment. So you will have a operating system running web server, and operating system running email server, and operating system running file server. So for example, maybe your company wants an email server that is completely run on Linux, while their web services and file servers they want to run on Windows. You can do that because these are all virtual environment and virtualized machines, and they can all run on top of the same hypervisor and share the same hardware here, as opposed to on this method, the dedicated server model. What's going to happen is you only have one operating system using all the hardware and available resources. And if it is, for example, Windows operating system, Windows Server 2019, and your company needs to install a Linux based email server or something, you have to get another hardware to do it because there is no virtualization done here. So that's why the virtualization configuration is very flexible, both in enterprise environment but also in small business environments. Type 2 hypervisors. A Type 2 hypervisor is a software that creates and runs VM instances. The computer on which a hypervisor is supporting one or more VMs is a host machine. Type 2 hypervisors are also called hosted hypervisors. So one of the big advantage of Type 2 hypervisors is that the management console software is not required. So that is one of the key features of Type 2 hypervisors. So you probably have heard Type 1 versus Type 2 hypervisors before, but if this is the first time you hear the Type 2 hypervisor, Type 2 hypervisors would have usually a graphical user interface, and you would install Type 2 hypervisors on top of your operating system. So you will have your Windows computer, for example, and the VMware workstation, for example, would be a Type 2 hypervisor. You would be able to use typically your mouse and keyboard and click on some buttons to create the virtualized instances. So you can run off Windows, Linux, and Unix, etc. Virtualized machines by clicking a few buttons and installing ISO files, the image files of those operating systems, and you would be using your computer to do it. It's like, you can have even Windows Windows 11 Home Edition or Windows 10 Professional or Home Edition, for example, and you can install VMware Workstation Pro, and you got a Type 2 hypervisor. As opposed to Type 1 hypervisor, that would mean that basically there is no operating system which the hypervisor will be installing on top of. Instead, the hypervisor would be directly installing onto the hardware. There would be no operating system right here. So what's going to happen is when you turn on your server, instead of you will have a your operating system being turned on, presented to you. You will be presented with whatever the hypervisor's management console software. That could be a web GUI in some cases, in most cases those are web GUIs actually. Things like Proxmox or EXXI, those ones are Type 1 hypervisors, so they would have a web GUI, but they would not be installing on top of your existing operating systems, and you would not be able to interact with like just another software. So think Type 2 hypervisors is like a software that you install on top of your current operating system, such as VMware Workstation Pro, and Type 1 hypervisors are directly installed onto the hardware, and therefore you will end up having a management console and you wouldn't have that overhead of operating system. One thing I would like to point out here that Cisco is not highlighting here is that the question, why would you want to use Type 1 or why would you want to use Type 2? So situations. So in most enterprise environments, you will be installing Type 1 hypervisors. You will be directly installing something like EXXI, VMware EXXI, or Proxmox or something like that directly to your directly on top of the hardware, and then you will be managing it through a web interface console. So that's what you most likely going to do Type 1 in the industry. The reason why we still use Type 2, however, is for laboratory purposes, sometimes for testing, and in some small business environment, you may end up using a Type 2 hypervisor to run their applications and virtual machines because it's cost effective and easier for their local IT department with very few people and very little knowledge to manage it, because it basically have a nice web GUI and it get installed on top of an already running operating system such as Windows 11, right? So those are the differences. Again, I have posted few videos on my YouTube channels in the past on VMware EXXI, which is Type 1 hypervisor, and VMware Workstation, which is Type 2 hypervisor already. So you can go ahead and check that out so that you will have an idea about what are the differences are. So Type 2 hypervisors are just like any other Windows software or a Linux software. Type 1 hypervisors are directly getting installed onto the hardware. Virtual network infrastructure. Type 1 hypervisors. So Type 1 hypervisors are also called bare metal approach because the hypervisor is directly installed on the hardware. The Type 1 hypervisors are usually used on enterprise servers and data center networking devices. With Type 1 hypervisors, that hypervisor is installed directly on the server or the networking hardware itself. So then the instance of an OS are installed on the hypervisor as shown in the figure on the bottom of your screen. So the Type 1 hypervisors have direct access to the hardware resources and therefore they are more efficient than hosted architecture. So remember on the previous model, we had the operating system such as Windows or Linux that we are installing the hypervisor on top of that. As a result, we're gonna have overhead, but right now we don't have that problem. So it is more efficient because the hypervisor is directly interacting with the hardware, as I mentioned in my previous slide. So the Type 1 hypervisors improved scalability, performance, and robustness. So keep that in mind. Installing a VM on a hypervisor. Type 1 hypervisors require a management console to manage the hypervisor. The management software is used to manage multiple servers using the same hypervisor. The management console can automatically consolidate servers and power on or off servers as required. The management console provides recovery from hardware failure. If a server component fails, the management console automatically moves the VM to another server. Cisco Unified Computing System, also known as UCS, manager controls multiple servers and manages resources for thousands of VMs. Some management consoles also allow server over allocation. So over allocation is when multiple OS instances are installed, but their memory allocation exceeds the total amount of memory that server has. Over allocation is a common practice because all 4 OS instances rarely require all the allocated resources at one moment. So what that basically means is the type 1 hypervisors, as I mentioned previously, need that management console to interact, right? Things like ESXi, you can watch my video on my YouTube channel. I am interacting with the ESXi type 1 hypervisor through a web console. But when I had some demonstration on VMware Workstation, which is a type 2 hypervisor, I'm interacting with the hypervisor on my Windows desktop using a graphical user interface and just by clicking using a mouse and a keyboard. So the same thing with the ESXi, because it has a web GUI, but actually the web GUI, the server itself is not located on my desktop. It is on a bare metal system. So that's what makes type 1 different from type 2. But however, type 1, as I mentioned, it is more efficient and it allows you to manage the things more efficiently because it is directly linked to the hardware with no overhead or operating system in between the hypervisor and the hardware, right? So that's what makes it so efficient. And little bit about over allocation, a little bit more about it. So let's say you have a couple of hypervisors, but you have only 32 GB of RAM. But one of your virtual machine may need all 32 GB of RAM at certain points, but the other virtual machine only need maybe 1 or 2 GB of RAM most of the time, but sometimes doesn't sit idle, doesn't do much at all, right? So that's what I mean by over allocating. So you can have all 32 GB of RAM allocated to one virtual machine. The other virtual machine will have, like, let's say 2 GB of RAM allocated. But as long as the two virtual machines are not trying to use up all of it at the same time, everything will run smoothly. But even if they try to access both at the same time, which is now 34 GB of RAM, which doesn't exist because your maximum is 32 and you have already allocated that to one virtual machine, the other one has 2, but now both are using at maximum. Most hypervisors, type 1 hypervisors, have the ability to negotiate that and provide a really good service without having any interruption. So again, I will go into depth of how hypervisors work on my hardware lecture course, but for now just remember that the type 1 hypervisors is a really good option to over allocation of resources when the multiple OS instances are installed. Keep that in mind. So you can over allocate resources using type 1 just for now, but I will explain the rest in depth. But just to give you an idea, you can have 2 operating systems, but both could have overuse of that memory. So because it's the type 1 hypervisors allow us to do that. The complexity of network virtualization. Server virtualization hides several resources. This can create problems when using traditional network architectures. Virtual machines are movable and the network administrator must be able to add, drop, and change network resources and profiles to support their mobility. So this process would be manual and time consuming with traditional network switches. So the traffic flows differ from the traditional client server model. typically there is a considerable amount of traffic being exchanged between the virtual servers. In this example, like what we are talking about in virtual servers is the east and west traffic that exchange in the location and intensity over time. North-south traffic is typically traffic destined for off-site locations such as another data center, other cloud providers, or the internet. So keep that in mind. So the north-south traffic is basically means going to off-site and to the inside. So east-west traffic means that you are within your site accessing across the different servers. So keep that in mind. So that's an important concept that you should learn as well. This is an example diagram that is clearly defining east-west traffic versus north-south traffic, but it is a broad concept applied to all network systems, that when you're looking at it from in terms of data flow and service flows. Okay, keep that in mind. So the north-south traffic is like in and out of your entire network through multiple layers like core layer, distribution layer, access layer, etc. And the east-west traffic is basically like the servers itself communicating against each other within one single layer, typically one or two single layers, without going through the core distribution layer. So that's what it means by east-west and north-south, because some of you, this is probably the first time you heard these terms, and this is exactly what those terms means. You should know this for your exams and quizzes as well as for your future career. The dynamic ever-changing traffic requires a flexible approach to network resource management. Existing network infrastructures can respond to changing requirements related to management of traffic flows by using quality of service, also known as QoS, and security level configurations for individual flows. However, in large enterprises using multi-vendor equipment, each time a new VM is enabled, the necessary reconfiguration can be very time consuming. The network infrastructure can also benefit from virtualization, so the network functions can be virtualized. Each network device can be segmented into multiple virtual devices that operates as independent devices. Example includes sub-interfaces, virtual interfaces, VLANs, and routing tables. So the virtualized routing is called virtual routing and forwarding, or VRF. So virtual routing and the virtualized network environment, I would say, is the next generation or next step of how we do network engineering. So this is basically allowing us much more flexibility than having a non-virtualized traditional network environment. So this is a really cool feature nowadays, because this is pretty much the next generation of network engineering. Software-defined networking. There's a video called Software-Defined Networking available to you through Cisco NetAcad. If you have access to Cisco NetAcad, please go ahead and watch it there. But if you do not, I have a copy of that posted to my YouTube channel. So I will leave a link in the description as well as a card on the top right hand corner. I would recommend that you watch this video before you move forward with the next few slides. Control plane and data plane. A network device contains the following planes: control plane and data plane. So the control plane, this is typically regarded as the brains of a device. It is used to make forwarding decisions. The control plane contains layer 2 and layer 3 route forwarding mechanisms such as routing protocols, neighbor tables, topology tables, IPv4 and IPv6 routing tables, STP, and the ARP table. Information sent to the control plane is processed by the CPU. Data plane, also called the forwarding plane. This plane is typically the switch fabric connecting the various network ports on a device. The data plane of each device is used to forward traffic flows. Routers and switches use information from the control plane to forward incoming traffic out the appropriate egress interface. Information in the data plane is typically processed by a special data plane processor without the CPU getting involved. This is an important concept that you should understand. So a network device contains two planes. They call the control plane and the data plane. And the control plane, you could look at that as a brains of the device, while the data plane is like the forwarding plane, and that is typically associated with switches, while the control plane is associated with layer 2 and layer 3 routing. And this is a really important concept because this is fundamental to how a networking device would work. CEF is an advanced layer 3 IP switching technology that enables forwarding of packets to occur at the data plane without consulting the control plane. So CEF is an advanced methodology that can be used to do the layer 3 IP switching technology without having to go through the control plane. SDN is basically the separation of the control plane and the data plane. The control plane function is removed from each device and is performed by a centralized controller. The centralized controller communicates control plane functions to each device. Each device can now focus on forwarding data while the centralized controller manages data flow, increases security, and provides other services. So on the right hand side, we have a control plane with a centralized controller, and then the data planes underneath it. The forwarding instructions are sent by that control plane, get processed by these data planes down below. So that's what it means by the SDN. So SDN is basically separating the control plane and data plane, and the control plane function is removed from each device, but now it is performed by that centralized controller. So that's what the SDN would do. So the management plane is responsible for managing a device to its connection to the network. Network administrators use the applications such as Secure Shell, which is SSH, Trivial File Transfer Protocol, also known as TFTP, Secure FTP, and Secure Hypertext Transfer Protocol, which is also known as HTTPS, to access the management plane and configure a device. The management plane is how you have access and configure devices in your networking studies. In addition, protocols like Simple Network Management Protocol, also known as SNMP, use the management plane as well. So the management plane is how you actually use the CLI of a Cisco device. That is management plane. So keep that in mind. So in your studies on previous CCNA1, CCNA2 courses, as well as in this course in CCNA3, we went through some Cisco labs and some examples, screenshots of those Cisco labs from CLI console images, like the screenshots. Those screenshots are actually taking the screenshots they are coming from basically the management plane, right? Because that's how we interact with those devices. Network virtualization technologies. Two major network architectures have been developed to support network virtualization. They include SDN and ACI, right? SDN, which is a software defined networking, which is a network architecture that virtualizes the network, offering a new approach to network administration and management that seeks to simplify and streamline the administration process. The ACI, which is a Cisco application-centric infrastructure, is a purpose-built hardware solution for integrating cloud computing and data center management, and it is a Cisco proprietary one, and in use in some enterprise environments. Components of an SDN may include the following: OpenFlow. This approach was developed at Stanford University to manage traffic between routers, switches, wireless access points, and a controller. The OpenFlow protocol is a basic element in building SDN solutions. OpenStack. So this approach is a virtualization and orchestration platform designed to build scalable cloud environments and provide an IaaS solution. OpenStack is often used with Cisco ACI. Orchestration in networking is the process of automating the provisioning of network components such as servers, storage, switches, routers, and applications. So that's the one of the mechanisms you can do with OpenStack. Other components. So the other components include the interface to the routing system, also known as I2RS, transparent interconnection of lots of links, also known as TRIL, Cisco Fabric Path (FP), and the IEEE 802.1aq shortest path bridging, also known as SPB. So those are some other options available in the SDN component architecture. Traditional and SDN architectures. In traditional router or switch architecture, the control plane and data plane functions occurred in the same device. Routing decisions and packet forwarding are the responsibility of the device operating system. In SDN, management of the control plane is moved to a centralized SDN controller, as I mentioned before. So the figure compares the traditional traditional architecture to the SDN architecture. So right here we have the traditional architecture. You have different networking devices such as routers and switches, for example. So we could have, let's say, multiple routers, and you have a data plane and the control plane, right, for each device. But in the SDN architecture, we have a centralized control plane with the SDN controller, and using OpenFlow, we have we have a centralized control plane up here. With the OpenFlow, we have data planes, different data planes on different devices connecting to that one single control plane. So that's the SDN architecture. So compared to traditional, the SDN architecture has a centralized control plane. The SDN controller is a logical entity that enables network administrators to manage and dictate how the data plane of switches and routers should handle network traffic. So it orchestrates, mediates, and facilitates communication between applications and network elements. The complete SDN framework is shown in the figure on the right hand side. Note the use of the application programming interface, also known as APIs. So how the application layer going to communicate with the control plane is using APIs. Those are called application programming interface, which I will introduce a little bit in detail further down this lecture. For now, and what you need to remember is API is a standardized definition of the proper way for an application to request services from another application. So it's a way of communicating between applications. Like basically you can look at it as like figuring out a common language between two different applications is what the API is doing. The SDN controller uses northbound APIs to communicate with the upstream applications, helping network administrators shape traffic and deploy services. The SDN controller uses southbound APIs to define the behavior of the data planes on downstream switches and routers. OpenFlow is a widely implemented southbound API. So the OpenFlow is a type of a southbound API. So this is southbound, and that's northbound. North is upward, south is downward. So that's what it means by southbound and northbound. And what we have discussed here on is shown here on the right hand side on this diagram. Controllers. SDN controller and operations. The SDN controller defines the data flows between the centralized control plane and the data plane on individual routers and switches. So each flow travels through the network must first get permission from the SDN controller, which verifies that the communication is permissible according to the network policy that you have implemented. All complex functions are performed by the controller. The controller populates flow tables, switches manage the flow tables. So the controller would is the one that going to be populating those flow tables, and the switches will be the one that going to be managing those flow tables. So population will happen at the controller level and the management happen at the switch level. So that's what's shown here on the right hand side with the diagram. So you have the open flow switch, and you have the open flow protocol is used over TLS, which is secure to the SDN controller, and that will be communicating across this network. So that's what it's seeing up here. Within each switch, a series of tables implemented in hardware or firmware are used to manage the flows of packets through the switch. To the switch, a flow is a sequence of packets that matches a specific entry in a flow table. So for the switch point of view, a flow is pretty much a sequence of packets that matches a specific entry in that table that the switch has, like an entry within that table the switch has, right? So 3 table types shown in the previous figure. So if you go back in here, you have 3 tables type, which are flow tables and the group tables and the meter tables, right? So these are 3 different types of tables right? So the flow table, this table matches incoming packets to a particular flow and specify the functions that are to be performed on those packets. There may be multiple flow tables that operates in a pipeline fashion. So you could have multiple flow tables interconnected like a pipeline, where each time it goes through the flow looking for a entry in the table, go to the next table and go to the entry. So those are like flow tables. Group tables, a flow table may direct a flow to a group table, which may trigger a variety of actions that affect one or more flows. So that's what the group table do. It's a group action. Meter table, this table triggers a variety of performance related actions on a flow, including the ability to rate limit the traffic. So that's basically like a traffic shaping or a QoS type of table, where it is actually doing performance related actions. You should know what these tables are and how they are differ from each other, so make sure that you understand this. There's a video from Cisco called Cisco's ACI. If you have access to a Cisco NetAcad, please go ahead and watch that over there. If not, I have a copy of that video posted to my YouTube channel. So I will leave a link in the description as well as a card on the top right hand corner. I would recommend again that you watch this Cisco ACI video first before you move forward with the next few slides. Core components of ACI. There are 3 core components of the ACI architecture. They include the application network profile, also known as APN. An APN is a collection of endpoint groups, also known as EPGs. Their connections and the policies that define those connections. Application Policy Infrastructure Controller, also known as APIC. APIC is a centralized software controller that manages and operates a scalable ACI cluster fabric. It is designed for programmability and centralized management. It translates application policies into network programming. Cisco Nexus 9000 series switches. So these switches provides an application-aware switching fabric and work with the APIC to manage the virtual and physical infrastructure. So the APIC is positioned between the APN and ACI enable network infrastructure the APIC translate the application requirements into a network configuration to meet those needs. The application-centric infrastructure is a type of Cisco methodology of handling, this type of networking infrastructure. So it is a Cisco proprietary one. However, you should be familiar with ACI even if you are not taking this particular course, because it is widely accepted and adapted in some of the North American networks and systems. So you should be familiar with this. So one thing keep in mind, the ACI is a Cisco proprietary method of handling network infrastructure. And here we have introduced you to the components associated with that, the three core components, which is the APN, APIC, and the Cisco Nexus 9000 series switches. So the application network profile would include the customer or tenant contract, the VLANs, in type of virtualization software such as the VMware, web services, applications, and the database. So that's what the application network profile gonna consist of. And then we will have the APIC, and below that you will have the switcher. So this is gonna be the hierarchy of the controllers, that how it's going to work, the Cisco proprietary ACI methodology. This is how it works. So this is the visual representation of the previous slide. So we have application network profile, and in between we have the APIC, and underneath it we have the Cisco switches that will be handling all of this infrastructure. Spine leaf topology. The Cisco ACI fabric is composed of the APIC and the Cisco Nexus 9000 series switches using two-tier spine leaf topology as shown in the figure on the right hand side. So this is called a spine leaf topology. The leaf switches attach to the spines, but they never attach to each other. So the leaf switches right here where it says leaves, those are attached to the spine, but they don't attach to they don't attach to each other. So there is no connection between them like that, but they are attaching to the spine as well as the ones right below the leaf, right? So but they don't interconnect across it. So similarity, so the spine switches only attach the leaf and the core switches, and in this two-tier topology, everything is one hop from everything else. So what the advantages of this type of topology is, every single device is just one hop from the everything else. So this is one hop from here, this is one hop from here, etc. So when compared to SDN, the APIC controller does not manipulate the data path directly. Instead, the APIC centralizes the policy definition and programs the leaf switches to forward traffic based on the defined policy. So the APIC's primary job in this situation is basically programming and centralizing that kind of programming and management of this network, as opposed to having manipulation of data paths directly by placing it in the middle of this system. So it's APIC is not in the middle of the network handling all of this data traffic and managing it. Instead, it is basically defining the policies and programming these switches to do its job based on whatever the configuration you're going to be setting up on the APIC. So that's what makes spine leaf topology a unique topology. SDN types. The Cisco Application Policy Infrastructure Controller, the enterprise module, also known as APIC-EM, extend the ACI-EM at enterprise and campus deployments. To better understand APIC-EM, it is helpful to take a broader look at the three types of SDN. So let's look at the three types of SDN, and then we will go back and look into what APIC-EM is all about. So we have the device-based SDN. So the devices are programmable by applications running on the device itself or on a server in the network, as shown in this figure here. So in the situation where we have the device-based software-defined networks, SDNs, we have the application, and then we have the data plane, 1 data plane, 2 data plane, 3 data plane, 4 data plane, 5, etc., etc., and we are using open flow between the application and the data planes, right? So this is how the the device-based software-defined networking, or SDN, works. The controller-based SDN uses a centralized controller that has knowledge of all devices in the network, as shown in this figure on the bottom of your screen. So in this situation, the applications can interface with the controller responsible for managing devices and manipulating traffic flows throughout the network. The Cisco Open SDN controller is a commercially distributed open daylight, distribution of open daylight. And so when we have the application, the open daylight application up here, we have SDN controller, which is the software defined network controller, and we have the data plane connected to this as shown in this figure. Again, this is also using the open flow methodology. The policy-based SDN, which is similar to a controller-based SDN, where a centralized controller has a view of all devices in the network, as shown in the figure on the right-hand side. The policy-based SDN includes an additional policy layer right here, applied right here, and the policy layer that operates at a higher level of abstraction. So this included, the policy layer is going to be in a higher level than the SDN controller itself. So it uses built-in applications that automates advanced configuration tasks via a guided workflow and user-friendly graphical user interface. No programming skills are required, and Cisco APIC-EM is an example of this type of SDN. So the advantage of policy-based SDN is that it can provide the user with a nice GUI up here that allow you to interact with it and configure it with very little or no programming skills required to do some advanced configurations. So this type of GUI, policy-based SDNs do still have the options for advanced users to use programming in there. So there are CLI access for those in almost in all cases, including APIC-EM, Cisco proprietary one as well. But it also comes with the web GUI, which is very user friendly and easy to set up compared to the previous ones. So let's look at APIC-EM. So APIC-EM features are listed here. So the Cisco APIC-EM provides a single interface for network management, including discovering and accessing device and host inventories, viewing the topology as shown on the right hand side here, and tracing a path between endpoints and setting policies. So remember, the web GUI, one of the advantages comes with this type of software defined the software defined policy-based method. So the policy-based software defined networks, well, this is that advantage, one of the biggest advantage. It has a nice graphical web user interface, or GUI, just like is shown here. So this is the Cisco proprietary APIC-EM web GUI, and you can see you can also trace your network, and you can see the network diagram and different devices, and you can click on these devices on here and then configure them accordingly. APIC-EM Path Trace. The APIC-EM Path Trace tool allows the administrator to easily visualize traffic flows and discover any conflicting, duplicate, or shadowed ACL entries. So if you don't remember what ACLs are and how ACLs operates, please go back to my YouTube channel and check those ACL lectures. So I will leave links in the description if I can, or I will put some cards on it. Make sure that you understand how ACLs work at this point. So what this tool, APIC-EM path trace tool is going to do, it's going to let you easily visualize the traffic flows and discover any conflicting and duplicate or shadowed ACL entries. So this tool examines specific ACLs on the path between two end nodes, displaying any potential issues. You can see where any ACLs along the path either permitted or denied your traffic, as shown in the figure on the right hand side. So right here we have the start point and the end point, and then between these devices, these are the ACLs that are configured, and it's showing what's happening on each of the hops or each of the time when the traffic sees those ACLs, meets those ACLs. So notice how the branch dash router 2 is permit all traffic. So branch dash router 2, it shows all traffics are permitted. So the traffic administrator can now make adjustment if necessary to better filter traffic on any of these hops. So right here we have the trace done up here, and it says trace successful, and then in this nice graphical user interface is showing those ACL configurations along the path of this trace. So in my opinion, this is the next generation networking engineering or network engineering. This is the next generation of network design, development and network engineering, because the software defined networking would be probably going to be taking over most of the applications where we use currently traditional network infrastructures. So as the time goes by, this is probably going to be a huge part. But however, I do not believe traditional network engineering going to be completely replaced for the next 50 to 100 years anyway. But the software defined networking will be a significant part of how we manage our network engineering infrastructure as of 2022 and moving forward. So keep that in mind as well. So that would bring us to the end of this lecture. I will introduce you to a few packet tracers files, as well as I will cover what we have gone over in this module. So there's a packet tracer file called the install Linux in a virtual machine and explore the GUI. If you have access to this packet, this is not a packet tracer file. This is actually a documentation. So if you have access to this documentation, please go ahead and do it. If you do not, I will try to find a copy of this document and post to my sanuja.com website, so you can download from there and do this particular activity. So here is a summary of what we have covered in this module. We learned cloud computing involves large number of computers connected through a network that can be physically located anywhere in the world. So the cloud computing can reduce operational costs by using resources more efficiently. The three main cloud computing services defined by the National Institute of Standards and Technology, also known as NIST, are software as a service, platform as a service, and infrastructure as a service. The four types of clouds are public, private, hybrid, and community clouds. And you should know what they are and the differences between them. The virtualization is the foundation of cloud computing, but the virtualization and cloud computing are not interchangeable words to describe each other. They are different concepts. Virtualization needs to be there in order for the cloud computing to work, but the virtualization itself doesn't need to have to be done on cloud computing, as I mentioned to you about like the desktop applications such as VMware Workstation. Virtualization separates the operating system from the hardware. So that is the primary purpose of a virtualization environment. The virtualization reduces cost because less equipment is required, less energy is consumed, and less space is required when you have virtualized different operating systems. It provides for easier prototyping, faster server provisioning, increased server uptime, improved disaster recovery, and legacy support. With type 1 hypervisors, the hypervisor is installed directly on the server or networking hardware. A type 2 hypervisor is a software that creates and runs virtual machines instances. It can be installed on top of the operating system or can be installed between the firmware and the operating system. We also learned the type 1 hypervisors are also called the bare metal approach because the hypervisor is installed directly on the hardware itself. The type 1 hypervisors have direct access to the hardware resources and are more efficient than hosted architecture. They improved scalability, performance, and robustness. So because there is no operating system dependability in between the hypervisor and your hardware, it is much more efficient. So you don't have to have Linux or Windows or anything installed in order to have your hypervisor running, because hypervisor directly being installed on the hardware itself with the type 1 hypervisors. The type 1 hypervisors required a management console to manage the hypervisor, unlike the web GUI, just general GUI that you get from the type 2 hypervisor. So you might get a web GUI with the type 1 hypervisor, such as VMware EXXi. Server virtualization hides servers resources such as the number and identity of physical servers, processors, and operating systems from the server users. This practice can create problems if the data center is using traditional network architecture. The traffic flows in the data center differ substantially from traditional client-server model. Typically, a data center has a considerable amount of traffic being exchanged between virtual servers, which are known as east-west traffic, and can change in location and intensity over time. The north-south traffic occurs between the distribution and core layers and is typically traffic or distant for off-site locations such as another data center, other cloud providers, or the internet. So remember the differences between east-west traffic and the north-south traffic if that question comes up on your Cisco exams. Two major traffic architectures have been developed to support network virtualization. Those includes the software-defined networking, which is SDN, and the Cisco application-centric infrastructure, which is a Cisco proprietary one called ACI. So the components of SDN may include the OpenFlow, OpenStack, and other components. And we learn a network device contains a control plane and a data plane, whether it's virtualized or whether it's traditional. And the control plane is registered as the brains of a device. So the SDN is basically the separation of the control plane and data plane. The control plane function is removed from each device and is performed by a centralized controller in the SDN situation. So the SDN controller is a logical entity that enables network administrators to maintain and manage and dictate how the data plane of switches and routers should handle network traffic. The data plane, also called the forwarding plane, is typically the switch fabric connecting the various network ports on a device and is used to forward traffic flows. The management plane is responsible for managing a device through its connected devices, so through its connection to the network. The SDN controller is a logical entity that enables network administrators to manage and dictate how the data plane of switches and routers should handle network traffic. The Cisco developed the application-centric infrastructure, also known as ACI, which is a proprietary Cisco methodology, which is more advanced and innovative than the earlier SDN approaches. The Cisco ACI is a hardware solution for integrating cloud computing and data management. Keep that in mind. The Cisco ACI is a hardware solution. At a high level, the policy element of the network is removed from the data plane. This simplifies the way the data center networks are created. We also learn the three core components of ACI architecture are application network profile, also known as APN, application policy infrastructure controller, also known as APIC, and Cisco Nexus 9000 series switches, which I have introduced to you on our ACI slides. So the Cisco ACI fabric is composed of the APIC and the Cisco Nexus 9000 series switches using two-tier spine leaf topology. Make sure that you know the differences and uniqueness of those spine leaf topologies. When compared to SDN, the APIC controller does not manipulate the data path directly. Instead, the APIC centralizes the policy definition and programs the leaf switches to forward traffic based on the defined policies. There are three types of SDN: device-based SDN, controller-based SDN, and policy-based SDN. We have briefly described what each of these types are when it's come to the point, like a basic overview of them. But the policy-based SDN includes an additional policy layer that operates at a higher level of abstraction. And the policy-based SDN is the most robust, providing for a simple mechanism to control and manage policies across the entire network, and the Cisco APIC-EM is an example of that policy-based SDN. So Cisco APIC-EM provides a single interface for network management, including discovering and accessing device and host inventories, weaving the topology, tracing a path between endpoints, and setting policies. The APIC-EM path trace tools allow us to easily visualize traffic flows and discover any conflicting, duplicating, or shadowed ACL entries. So basically, you can use this tool to examine specific ACLs on the path between two end nodes, displaying any potential issues. And this is a really neat way of administrating a network. And again, as I mentioned previously, I believe software-defined networking would be the future of network engineering. If you like these type of lectures, please thumbs up this video and subscribe to my channel. If you have any questions related to any of the topics that we have covered in this module, don't hesitate to reach out to me. Please go over all the key concepts that we have covered today before you take your Cisco exam or quiz. Until next time, good luck with your exams and have a nice day.